Hi everyone, welcome to Machine Learning from Data. This is lecture 26, part 1. In this lecture, we'll talk about something that's known as kernel machines. We are already familiar with the term kernel, and we are going to dig deeper into that and understanding its application, some of the important kernels that exist in most applications today, why the kernel and how the kernel actually measures similarity and how it stands against similar to many other already known models. And in the end, we look at some important applications of kernels. So let us begin. In the last lecture, of course, what we introduced was the dual version of the optimal hyperplane problem, and it allowed us to implement the entire algorithm by just computing the dot product. So that was the important accomplishment, I would say, of last lecture, where we can utilize this kernel that was defined by K that was essentially doing nothing but just computing dot products. So the dual version is also a quadratic program, as we can see here. And here is the non-separable data version shown such that we are allowing some penetration depending on the value of C, which is nothing but like a regularization parameter. So basically C is like a trade-off between margin violation and the size of the margin. Larger C is more is putting like more focus on in-sample error, if you want to think about it, right? And so if like C is smaller or less, so then you are allowing margin violations essentially. And C is essentially a regularization parameter in the sense that if you're focusing more on C, that means your classifier is more regularized, right? And this dual version of the problem allowed us to work in higher dimensions. That was more important because all we needed was to get the dot product, the inner product, using the kernel, right? And then we saw this example with non-separable data such that one of them was using the pseudo-inverse algorithm, which was like here, and we can tell a lot of overfitting. But with SVM, or like the algorithm that we saw here, with just like very low number of support vectors for this particular classifier, we could effectively get like a very effective classifier as such, right? So fewer effective support vectors lead to lower complexity, and this suggests we can work in large dimensions without losing control of E out, which was one of our concerns when we were moving to higher dimensional space, right? So using some appropriate kernel, we can save on computational costs, right? Computation becomes easier, and we are able to work in higher dimensions once we started to work with the dual version of the problem. And because like that turned out to be a quadratic program, we can easily solve it, and it takes somewhat this form, right? So we looked at that, like this is the final hypotheses and why B was calculated and how B was calculated. Okay, so a few more things from the previous lecture, of course, because we'll build on that today. So we specifically looked at the second order polynomial kernel, right? And here, all we had to do was like compute the dot product by not really going into this transformed space, but just like by staying there, by calculating this. And eventually we got to this final value of the kernel when we were calculating in Z space by actually not going in Z space, but staying in X space. And then we found out that the Qth order polynomial kernel looked it took somewhat similar form as this here, except that we have like a higher order there. And these are like two different forms of the Qth order polynomial kernel, and we'll see more forms today. So either one can be utilized, essentially depending on how we are computing the dot product, right? So here, this one has like a constant existing there, and so that's the inhomogeneous kernel. That's the word that's used for that. And this is the homogeneous kernel. Again, both of them are Qth order polynomial kernels, essentially. And why were they so important? They were important because they were saving us this like expensive computational cost that might exist if we actually went into the Z space and did all the computation, especially when Q is large, right? In that case, and that's what we are hoping for. So when Q is large, this becomes computationally inefficient. The second thing that we looked at, the second example that we looked at was the RBF kernel. So if you're getting confused by why like we never saw that, remember the Gaussian kernel that's also known as this, and we saw that one, right? So the Gaussian kernel is nothing but the RBF kernel. This is also known as the Gaussian kernel. So we could get these dot products in infinite space, as you can see here, right? And all we had to do was do this like computation in X space using some parameters, essentially using this expression, right? And in general, a d-dimensional RBF kernel looks something like this. All right, so you see this extra gamma term, which is nothing but a scale parameter. So essentially, if the scale is small, then like the radius is large, and the opposite is also true. So when like the scale is large, the radius is small, right? So what that means, and that, so that's like one, and the other, so the application of this RBF kernel is shown here on the digits data, right, on the right hand side, where we have utilized the regularization parameter that I talked about, right? So basically, there are two parameters that play a role in the final result, first of all, right? If, as I said, C is large, that means we're talking about the hard margin problem, which is this, right? And if C is small, that means we are focusing on more on regularization and less on EN, right? So that's the other extreme. And then this is like somewhere in between where we have like kind of working with a medium level C, where we are trying to like balance both, right? And with a slight change in like gamma and C, we can see the final classifier and what happens to the final classifier, right? So let's analyze this a little bit, right? So like with this particular kernel, there are two parameters that are important. The one is the gamma, of course, and then the other one is like the regularization parameter that's there, that we just talked about, right? So let's focus on this gamma because that defines the kernel, right? So this is like choosing the RBF kernel width. This is what this is telling us. This gamma is nothing but, as I said, a scale parameter that is representing width. So if this width is small, that means the scale parameter is large, and you will get a smoother classifier, right? And for medium ones, you will start to get, sorry, these regions of like higher fit, where we are like not really getting a smooth classifier, but we're really trying to um, get regions of different classification, right? So there's regions surrounding each point. And finally, with a very large gamma, which is this here, right, you can see extreme overfitting in some sense, right? So then thinking about this example with the digits data, we can tell that this RBF kernel is extremely powerful in the sense that, number one, it was allowing us to work in infinite dimensions, which is what we saw in the previous lecture, by setting two parameters only, right? And let me reiterate, there were only two parameters, C and gamma, right? And C was the regularization parameter, so that will help us allow the amount of regularization that we are allowing in infinite dimension. Of course, we need to focus more on C because rather than the margin violation, and you can tell why, because there are higher chances of overfitting. You can fit almost, like it's non-falsifiable, as we said. You can fit almost all data, right? The second parameter is the gamma, which is like the width of the kernel. So because we never physically transform into that Z space, we don't really know the right scale parameter if you think about it. So this is important because it's usually like one standard way of selecting this is by using cross-validation, of course. That could be one, but we have to be extremely, I would say, cautious when selecting this one because we don't actually go physically into that space, but we're doing all the computations in our space, in the X space. Okay, so this was just like a practical demonstration of the RBF kernel when applied to digits data. Let's dig deeper into this. As I said, let's talk a little bit more about this RBF Gaussian kernel in infinite dimension and what are some of the properties of that can be made relatable to some other models that we have looked at, right? So let's focus on this one. And I know that the kernel K for any two inputs, X and X prime, is going to look something like this. So let me go back. Yes, e to the X minus X prime. Let's assume that the scale parameter in this case is 1, right? Why not? So we're just assuming that this is like a standard case where my scale parameter is 1 or it's not there, right? So minus right? Okay. Now, going back to the optimal hyperplane problem, when we solved the dual version of the optimal hyperplane problem, we got the alphas, which were the optimization variables, and those alphas were the optimal alphas, right? I think I have the problem. So yeah, here, right? So we got this equation, and let me rewrite that here, right? So this is my final hypothesis that I got, which is g of x, some summation, and then alpha n star, the optimal, yn, and some kernel. So I'm assuming that I'm applying this kernel here, x plus b star, right? So b star was calculated, of course. And then let's say this is a classification problem, and so I have like here, it should have been like sine, right? I didn't leave enough space, but that's understandable. All right. So when we are thinking about these alphas, right? These alphas have this constraint that these alphas are usually greater than or equal to 0, right? And the ones where alpha n's are equal to 0 are the ones that we discard. Why? Because we take only alpha n that's greater than 0 for classification, because because those are the support vectors, right? So we can also allow like C alpha n if like we are allowing some penetration, but that's like a more generalized case. So let's stick to this scenario where we are allowing only alpha n as such, alpha n star greater than 0, right? So some summed over that, alpha n star greater than 0. And so let me like also substitute the kernel value and write it again. So basically what I'm trying to say is this is summation alpha n star greater than 0, right? Alpha n star yn, and then the kernel value actually, so which is e to the minus x bar squared. All right, so squared plus b star, of course. I just like substituted this here, right? And yeah, so this is my final g of x, sorry, g of x is here with, yeah, I was just thinking of whether I should rewrite the value of b or not, but I think that's already known how we get it, right? So we talked about it last time, we know how to get b. So that's fine, let's leave it as it is. Okay, now let's revisit the RBF network. If you remember the RBF network, let us revisit that. So the RBF network has my g of x equals sine the bias term, of course, plus summation j from 1 to k. Let's say there were like k a number of clusters, e minus x minus mu sub j, where mu sub j was the centers for each of these j's squared, right? So this is how my RBF network looks like. Now, if you compare both these equations, I mean this one and this one, if you compare both g of x's, they look pretty similar in the sense that this term is similar to this one in the sense that this is also a bias, right? So this can be thought of as like some b value, so it's similar to my b star value, this one, or b value in general, right? And then we also have the weights multiplied to this kernel, which is what my RBF kernel looks like. And we can think of these, and also when we go back to the optimal hyperplane problem, this is actually the weights, right? Weights for all my, so this is like, this can be, I'm not saying that this is WJ, but this can be thought of as like somewhat analogous to my WJs, because this is also in some ways calculating the weight, right? And this is similar to my kernel. Sorry, this one here is similar to my k, because this is k and this is k, except that instead of like this x prime, I have these like mu j's, right? So if we go back and think about these x's here, or x minus x prime, whatever we are writing here, it shouldn't be x minus x prime anymore. It can be like xn, sorry, minus x, isn't it? Because this is the kernel for like the nth point. Xn minus the data point, right? So this can be thought of, this xn is very similar to my mu j, right? The centers in my RBF network, because I'm trying to find the similarity of this point with respect to that point, right? So mu sub j is very similar to my x of n in my original. So essentially, the point that I'm trying to make here is like that both have a bias, and then the sum of the weights is multiplied by some similarity measure. What is the similarity measure? Well, similarity measure in both of them, in the like this exponential to the something minus something else squared is essentially measuring some similarity of this point with respect to this. And that's exactly what we are doing in my RBF network as well as in my original optimal hyperplane problem, right? For the RBF network, we said like we have to figure out K's, right? Then the clusters, and then and then we construct these centers, which is mu sub j's, right? And then these mu sub j's, like if this was x and this is mu sub j, these were, I would say, constructed using unsupervised learning, right? My centers were found using some unsupervised learning technique. And then my weights, my W0, Wj, all of them, all the weights, were eventually a result of the fit of the linear model, right? Fit of a linear model, depending on like what problem we are looking at. Now, if you look at the kernel method, K is essentially signifying this K, if we are trying to kind of compare both of them, is the number of support vectors, but it's like determined implicitly, right? So when we solve this optimization problems, it tells us the alpha values that are the support vectors. And only the non-zero ones are there in my equation, right? So that means these non-zero alphas or non-zero Lagrangian multipliers are exactly the number of terms in the summation. And then if you think about it, these are like corresponding to the centers of in my RBF network. So the centers are the support vectors, right? So centers are in some way equivalent to my support vectors, right? So we can view the optimal hyperplane kernel machine system, as I'm now calling it, because it is like a system with a lot of components. And that we can view that as the RBF network, where the number of centers have already been set because they are my support vectors and they're implicitly set. That's why I said they're implicitly set. And even the position of those centers have already been determined because they are my support vectors. They are the outcome of my original problem. So once I have the kernel, once I have the definition of a kernel, which is obviously similarity based in this case, once I have that, I have an RBF network with an already determined centers, already determined, number of clusters in some ways, and the centers through my support vectors, right? So I already have an RBF network, but even better because now I'm like really, I don't have to look or construct anything. The result of my, like the solution to the optimal hyperplane problem is already providing me with that, right? So this was to establish that there is this analogy that can be drawn between the kernel method, depending on like what kernel we choose. Depending on that, we can derive this analogy. So again, it depends on the choice of the kernel. I'm going to show you another example before we end this video, and that is to look at the neural networks. So let's look at neural networks in general, and I'm looking at like a two-layer neural network. All right, so let's assume we have like the input layer and then some output layer with a bias term as well. And remember this here, like whatever we are creating, each of these is a perceptron coming from like whatever the input layer I have, right? So essentially we'll have like more. So these are perceptrons. Let's say we are denoting them by like V1, and this one is V2 and so on, right? And then eventually I'm looking at a two layer. So I'll just like end my layer here in the sense that I'll have a summation with a sine function or whatever function I'm using here. And of course there will be some function here which converts my input perceptrons into some sort of signal. And usually, as we said earlier, this has to be a sigmoid, usually a tan h. So let's stick to that, right? Let's say it's a tan h, right? And then eventually you get this h of x, which is like sine of something. right? All those things here. And let's actually write the exact what it will be. So that will be, let's say these are the W's, right? So W0 and then all the other W's, right? So I'll have W0 plus the summation of, let's say these are M terms, M here. So I'll have I is from 1 up to M, right? Wi's, and then I have to multiply each of the W's by the output of like the sigmoid, so which is going to be my tan H. And tan H in turn will have like the perceptron here, right? So Wi transpose X, and that's it. And like consider this Vi transpose X as like having that augmented term as well, right? So let me call it new for now, but just remember that we used to have that augmented, or like V0 or something. Just don't want to confuse, right? So consider that this has that augmented already. So what exactly are we trying to do here? Well, it turns out that we can simulate, or we can again draw an analogy between the two-layer neural network by choosing an appropriate kernel using our original optimal hyperplane algorithm. So let's see what that kernel is going to be, or what that kernel could be, right? So I don't have enough space here. Let's begin by defining the kernel for X and X dot. Remember, because that's all that is to the optimal hyperplane problem. Like as the moment I can identify a kernel, I'm just like good to go, right? So let's have identified this kernel, which is tan H of X transpose X prime, right? And to make it like really generalized in terms of its application, let me have like some constants applied here, right? So these are some constants. And you can argue that this might not be a valid kernel for all choices of like my mu and C, of course, and there is like a lot of literature on that. So you can go and try to like find out what are those values for which this is not valid. But for this exercise, for this problem, we are just trying to draw the analogy with the kernel approach and the neural network. So let's stick with this, right? So essentially a kernel is nothing but a function of X and X prime. And so we have it, right? Like similar to this in the RBF network, we took some distance measure between X and X prime, right? And then we did like e to the minus distance squared. In the polynomial kernel, right, we did some form of, let me remind you, C plus X transpose X prime to the Q. And so you can say that this one is somewhat similar to this one, right? I mean, at least this basic term is looking like very similar. And so this one here is known as the neural network kernel, or the neural network kernel. So let's really try to put it into my g of x for my optimal hyperplane problem and see what happens, right? So if I do g of x is the sine summation alpha n star greater than 0, and then alpha n star yn tan h c, now x of n, right? X plus nu plus my b star. All right. So how is it very similar to what we just saw here? Well, we can draw analogies just like we did with the RBF network, right? This term here is my Wi's, right? And this is my W0. There is no second thought about that, because this acts like a bias, and that's exactly what my B star is doing here. Now what remains is this like tan HC, the term there. Oops. And then we have like this tan H with Vi transpose X plus V0, right? So if you focus on this term, Vi transpose X, right? And we go back and look at this, oops, not this, CXN transpose, right? It's a vector that's multiplied by X, and then my Vi transpose X is doing somewhat similar, right? And then my nu is some constant, which like we decided my V of 0 is also doing somewhat similar, right? So essentially in my neural network, if we go back and see these VIs initially, these are the ones that we tune. And then M has also to be fixed. M is like the number of nodes here, right? And in support vectors, or for example, in our optimal hyperplane problem, the number of support vectors is actually corresponding to the number of hidden nodes, because this is the summation that I have here, right? This is the summation I have that corresponds to the number of my total support vectors. So my support vectors are already giving me the number of hidden nodes, right? So number of hidden nodes. Well, that's excellent, right? So we don't need to choose this. In my problem, in my optimal hyperplane problem, this gets automatically set, and like in the optimal hyperplane algorithm with this particular kernel. Now the feature transform that's implemented by my first hidden layer is like automatically determined and is related to the support vectors. So by creating this analogy between neural networks and support vectors, right? We can say that support vectors can simulate a two-layer neural network, which can theoretically solve any problem. Like a two-layer neural network is enough to solve almost any problem. So you can implement it, right? Using, you can implement any kernel, I would say, as long as it is positive, definite, and symmetric, right? So as long as it is positive, definite, and symmetric, as we talked about last time as well, right? And in this example, in the neural network example, not only we have determined the number of hidden units, but we have the optimal fit, which is even better, right? So in summary, I would say support vector machines with the kernel trick can implement RBF network and neural networks. Basically, we are solving a convex optimization problem with this optimal hyperplane, right? Which is non-iterative and so almost exact. So that's the benefit, as long as we can figure out like a suitable kernel and appropriate kernel, we are actually in a better position when working with neural networks and RBF networks. So now this is a very powerful tool, the kernel method, and we will try to understand what exactly is the kernel. So we're going to take a deeper look at it in the next video.